You're in the RustZone, writing trusted applications in Rust talk. My name's Eric Evenchick. We're at Black Hat Asia 2018, and we'll get this rolling along as some people file in here. Just a little bit about me, what I do right now. I'm a principal research consultant at Tretis Partners. We do lots of pen testing type stuff, other security consulting. Big focus on mobile and embedded, so that's kind of how this whole TrustZone thing became interesting to me. And I also have this little side gig where I build some open source hardware things with this company called Linklayer Labs up in Canada, and we make some tools for hacking cars and stuff like that. Just a little outline of what we're going to go through today. We'll start off by talking about trusted execution environments and what they are and a general idea of what that is. We'll talk a bit about ARM TrustZone in detail just to show how that works. We'll go through some of the challenges that we've seen historically with these types of systems. We'll talk a bit about the Rust programming language. We'll slam Rust and TrustZone together and see how that ended up working, and then we'll do a little demo of that and take some questions. So let's start with trusted execution environments, which is a pretty general term. So what is it? One generalized way of describing it might be an isolated environment within a processor for performing secure operations. So it's some little isolated world that has some sort of segmentation from the rest of the processor where you can do operations and have some guarantee of that separation. And typically we see segmentation of three things: code, data, and hardware access. Code being that you can only run code, only stuff running in the trusted environment can run code inside of the trusted environment. Data being things like memory protection. You don't want the non-trusted world to be able to take a look into the secure world. And hardware access, this is especially useful in embedded applications, but you might actually restrict things to say, this really important general purpose I/O pin that launches the missile, only the secure world's allowed to toggle that GPIO pin and nobody else. Seems like maybe a good idea. You'll also see it in most computers nowadays in things like protecting the SPI flash that your processor boots from. To get your computer up and running, it has to read off this flash chip. And that can only be written to in certain special ways. And the reason for that is to prevent permanent backdoors of computers. If someone gets root, they can't take over your entire processor forever. Though sometimes they can, and there was a great talk last year about that actually at Black Hat Asia. And it's a combination of hardware features and software that make these types of things work. You need some hardware features to actually do the segmentation, and then you need software that's going to be able to run in these things and expose the functionality you want. So what do we have today? Well, the most common stuff, AMD, Intel, and ARM. So AMD has PSP, Platform Security Processor. Intel has their TXT, Trusted Execution Technology, and Software Guard extensions, which are some hardware features that are built into their chips. And ARM has TrustZone. And really we're going to focus on TrustZone today. Software-wise, there's a number of operating systems that you would run in the secure or in the TrustZone world. Three pretty common ones are Trustsonic's Kinibi. I believe Samsung devices use that quite a bit. There's Qualcomm QC, which I can almost guarantee that somebody in this audience has in their pocket right now. If you have a modern phone that's with the processor made by Qualcomm, it's probably running that. And then you have OpTEE, which is a free open source one and will be the subject of this talk, because it turns out that the closed down ones are A, expensive, and B, covered by NDAs. So we can only talk about the open source stuff. But the use cases for this, there's quite a number of them. Authentication is one that we see in Android. Every time you unlock your phone, actually, you're calling into this trusted world. And the reason for this is we can store things like credentials in a trusted environment, and we can actually segment that away. So if somebody gets root on the device, there's still this other layer of protection. And that's really a theme of these systems, is they create this extra barrier beyond just root. Financial applications, you'll often see trusted environments that are integrated into things like NFC systems. And the reason for this is they don't want to expose these secret keys that are being used to do transactions to just anybody. So they'll keep it in a little trusted secure world, and they will not let you know what the keys are. They'll just give you an API to make payments. Secure boot, we've seen it used for. Basic idea here is that you can start up in sort of a secure context, do some validation, and then switch over. And your code that's doing that secure boot chain shouldn't be impacted too much by the normal world, unless someone finds an issue. DRM applications, so probably the most prevalent one of DRM that uses a trusted application is WideVine, which is on most Android devices, unless you have some special home-baked version of Android running. And that's a DRM tool. The reason for DRM is what you're trying to do here is protect assets in a device that somebody owns from the person who owns it. You don't want them to get those DRM keys because otherwise your DRM model isn't so good anymore. So you can place those in a secure place, not let them access the keys, but then just give them an API to, say, decrypt content that's encrypted. So all this provides this additional layer of protection from the user and from the host OS. So again, you get root and you still have this extra thing you need to get through in order to get all those functionalities. And protecting the system from the user, sometimes we look at that and we put a sad face beside it because when it's a hacker conference. I mean, people don't like DRM all that much in this world. It's a reality, but that is often a goal because if someone can root a device, that's one level of access, but can we add more barriers? So one example of how this works for Gatekeeper on Android, definitely a simplification of it, but you have the lock setting service that communicates via Binder, which is the inter-process communication within the Android high-level operating system. And that's going to talk to a service, which is called Gatekeeper service. That ends up kind of going down through the, eventually makes it to a kernel module through the OS. And then that last layer is it actually has to talk through a IPC channel to the trusted execution environment, which might be QC, in which case you're talking QC-COM is the name of that IPC channel, into the Gatekeeper application. And that's actually running in this secure world, this trusted execution environment, and it's in its own little domain. So that's an ARM example, and ARM TrustZone, again, the thing I'm going to focus on. What is it? Well, it's ARM's trusted execution environment, and really what it defines is two worlds. This is not a term I came up with. It's literally what ARM calls it. You have the normal world and the secure world. And your normal world will be your rich OS, your Android, your Linux, your QNX, whatever it is that you want to run. This is the thing that the user is going to interact with. It's probably your UI. It's all your network stuff. All the nice rich features. And then your secure world is going to be a limited operating system that runs what are usually called trusted applications. And so this looks kind of like a real-time operating system in a lot of cases. Examples, again, are QC, opt-T, and some other things. And that world is, where you're going to do these operations that are secure. Now, we need to flip-flop between these two in order for them to be useful. And the way that this works is the processor can do a world switch. Again, that's the ARM term. So you start off in the normal world and you can set a bit and you can hop over to the secure world, do some stuff there, and hop back. And in practice, there's APIs that are built out across this boundary. So you can put a command in to request that some trusted application do some task. It'll switch worlds, it'll give it that information, it'll do whatever you asked it to do, and then it will give you some results, flip back, and those results will be ready for you to pick up and do something with. But the other key is all this is actually kind of useless without the last point, which is this lets you configure the processor will have options that lets you configure it so that only certain things are accessible in certain worlds. And without that, yeah, you have two worlds, but they're the same. But what we can do is actually restrict access to hardware, access to memory, and access to code using processor features. It's a little tough because those restrictions are actually not part of the TrustZone standard. They're specific to whoever made that chip. So the way that NXP does it versus the way that TI does it versus the way Qualcomm does it will be different. And what's even more frustrating is that information is almost never, with the exception of maybe Atmel, almost never in public documentation. They want you to get their security reference manual, and their security reference manual probably means you need to be a decently big client, and you need to sign NDAs, and then you can't talk about it. So it's a little tough to actually do that if you're just trying to do it for fun. But let's look at sort of an in-practice example. This is taken from the GNodeOS documentation, but it's a nice graphic of what happens whenever you're dealing with the normal world and with TrustZone. So we're in the normal world, and we have our CPU core. We have some instruction data cache. We have some L2 cache. We have some RAM. We'll notice on the CPU there is a secure configuration register. And that last bit at the very end is NS, which actually stands for non-secure. And so when non-secure is 1, you're not in the secure world. It would be nice if we could solve all our security problems by just setting not secure to 0, but it's a little more complicated than that. So what we end up with is also access to peripherals. So Ethernet, USB, MMC, GPU, and UART peripherals are accessible from this normal world. And so when we're running our normal code, Android, Linux, whatever it is, it can do Ethernet, it can do USB, talk to the GPU, it can talk some UART, but it can't access some of the other features. Then we do our world switch into the secure world, and we have different pieces of memory, which is going to be enforced by the MMU depending on that particular implementation that particular chipset has. But you'll have some memory segmentation, so you'll notice that those blocks are different than those blocks. You get your own protected piece of RAM. And you'll notice that we switched the bit to 0, so we are in fact in the secure world. And then you'll notice that we have a different set of peripherals that's available. Things like real-time clock, GPIO, graphics, and I2C. And one example of how this might work, let's say you have a device and it has something connected to I2C. You don't want users to be able to just interact with that in any way. You want them to have to go through an API that you designed, and they can only do very limited operations. For example, maybe this I2C device is like a secure coprocessor or does some signing, something like that. It's important. So what you can do is write a trusted application that exposes the functionality that you want them to be able to use, and then force them to use that, because otherwise they just cannot access the I2C peripheral. And that's enforced in hardware. You'll also notice the security controller becomes in scope in the secure world. This is another really common use case, is that there'll be a security controller that has the ability to do encryption or decryption operations using hopefully keys that are stored in it and not readable by anybody, but some keys you want to keep secret. So it's an encryption or decryption oracle. And this way you can protect that from just the average user sitting on the box by putting it in that second world. And so in practice, that's kind of how it works. You end up having an application in your normal world that needs something from the secure world. It's going to set some stuff up. It's going to do a world switch. Then that application in the secure world is going to do its thing. It's going to take the data. It's going to run. And then it's going to switch back along with providing some results. And you just keep doing that for every single secure operation you want to do. More or less how that works. But there's some challenges to these things, and they look a lot like the other challenges that you see anytime you're doing embedded stuff. But the reality is that there's no magical silver bullet in security. There's no one tool that solves everything. So you get the usual problems. And one is the actual OS that you typically run in here is usually very limited. There's a good reason for this. It doesn't need to do much, so you don't want it consuming all your resources. You don't want to run like a full Linux in there or anything. Also, it's supposed to be secure, so you don't want it to be this full rich OS. You want it to be a very limited, really stripped down to just the features you need. But in terms of protections, because of that, they tend to be a little light. So address space layer randomization is rare. There's a few that do it. It's questionable whether they're enabled on all devices. There's also the problem that they only have a small amount of address space typically, so there's attacks that you can do where you just kind of brute force the thing and hope for the best, and some of those are actually feasible just because the address space is so small. Things like stack canaries and guard pages, protections that we've been using for a very long time, aren't really used. And this kind of leads to the question of, is our secure world OS less secure than our normal world OS? Maybe. It does have sort of less OS level protection features. And then the other problem is that we don't get high-level language support. And we're going to write C. We're basically writing ARM assembly in C. That's how this stuff works. No Java, but I don't think anyone's complaining too much about that. But that's just how that works. But of course, that leads to the next part of it, which is writing good C is hard. This is no surprise. We've been talking about this for many years, but you have things like buffer overflows and use after freeze, memory problems that come up. You have typing issues whenever you're passing stuff around as void pointers. One thing I love about C is that the word void means nothing, but it also means everything. And it just so happens that syntactically that works. But you're passing stuff around, and it's hard to guarantee that what came in is what's going out. Compilers typically don't help you too much. Depends on the compiler, depends on what flags you have enabled, of course, but often most things will compile, unless you have like actual syntax problems. Usually it compiles. You might get warnings, and maybe your company has some policy about linting or about warning checks. In practice, enforcing that can be kind of tough. Depends on how mature your organization is in doing those types of things, but it's not always easy. And programmers can do silly things, and this again comes down to organizational, what you allow. But things like mem copies and stir copies and sprintfs. We have this kid here telling us that all his friends are using stir copy, but he's not because he understands how dangerous it is. And that's just something that's hard to avoid. You can audit code, you can make sure that people don't do it, but that's a secondary protection. It's like a process level protection as opposed to a language level thing. So that's just a challenge that you got to deal with. And sure enough, bad things happen. One example that I like is WideVine, the WideVine trusted application, which is in most Android devices, as I said. It's the DRM media server for that. It does decryption of DRM content. And what happened here was somebody decided to take a look at this trusted application, and whenever you run one, you got to call a command on it, basically. So it's got command codes, and you say, I'd like to decrypt this buffer. Here's a pointer to the buffer, and whatever. And that'll have a command code with a number. He noticed there was all these command codes that were not documented anywhere else and not used by anything on the system. So that was interesting. And then it turned out one of these was like a diagnostic command meant for debugging and testing, and it had there's just a good old-fashioned buffer overflow in it. And through that, it was able to get actual code execution in the secure world. So if you had access to that WideVine service, you could, call that particular command, and you'd be able to actually, do an overflow and execute code. There's more info. These slides will be up right after this, but there's more info on that, which it's a pretty cool write-up and a pretty neat vulnerability, I think. Another one, which it turns out there's a lot of pictures online of people smashing Samsung phones if you do a Google image search, but it wasn't a Samsung phone. And it was a one-time password buffer overflow. So the Samsung Knox security tools had this feature where you could generate one-time passwords. Any user was able to access the service on Android. So if you were any user on Android and SE Linux and everything allowed anybody to do it, you could ask it to generate a one-time password for you, which doesn't sound that bad. The problem was that whenever you pass it some data to do this, there was a buffer overflow in the parser for that. So, any user can now do a buffer overflow inside of the trusted world. The example of this, it was actually a Google Project Zero finding. It, they basically got it to crash, and they said, yeah, there's a bug, we need to fix it, or Samsung needs to fix it. But that was one that did come up. I don't know if there's actually any exploit of it in the wild, but at least the bug was proven, and it is a real thing. So that's some of the challenges, and now we're going to totally switch gears into talking about a programming language. The goal of this talk was sort of to introduce you to the concept of trusted execution environments and TrustZone, then just use Rust a bit, and then put it together. So we're at sort of Act 2. And maybe some people here have heard of Rust. Maybe they have some interest in it, which is why they showed up here. But really briefly, it's a new systems programming language. And when I say new, I mean new compared to other systems programming languages. So it's a little newer than C. It started development in 2010. It's sponsored by Mozilla. Mozilla does, a lot to push the language forward, and they're using it extensively in some new web rendering. They have a new web rendering toolkit called Servo that's written in it. So yeah, they're backing that horse. The cool thing for it is it works for embedded, like some languages don't. If you've ever tried writing something like Python and you want to do it on an embedded system, well, there are interpreters like MicroPython that will allow you to do that, but you can't actually write Python code that will, run with no other dependencies on an embedded system. It just doesn't compile down. So you also have things like Go, which is a compiled language, but it has runtime dependencies and things. So you still need some kind of basic operating system to make that thing go. With Rust, you actually can use no standard library, and once you do that, you don't need libc, so you don't need an operating system. It'll compile right down to bytecode. There's no default garbage collection or runtime that you need to bundle with it, so you can do real-time things and not have things like garbage collection pauses. And yeah, that's more useful for real-time systems, but it's interesting. And raw memory access, which most languages, you can find a way to do it, but it won't be exposed to you in a nice way. Embedded, when you want to set that bit in that register, you need to actually be able to flip the bit, and so you need raw memory access to do it. So why might we use Rust for this sort of thing? Well, there's a lot of safety features that Rust was designed to implement, and the big ones are these compile time memory checks. So it's checking for memory safety at compile time. There's a lot of ways that this is implemented, and it would probably be there are entire talks about how this works. But one way to think about it is things like borrowing. So the ownership of memory is tracked through the program, and it has to be, released from certain places before it can be used. It's almost like you have something like a mutex. But this is happening at compile time. So you don't take performance hits on this, and if you fail to write code that follows the Rust standard for borrowing and freeing memory in the right ways, it just won't compile. It'll give up and give you errors, and honestly, when you first start working with the language, it's the most frustrating thing ever, because you're looking at it and you're like, that makes perfect sense to me, why won't it compile? And you get an error that's like, this is not mutable, or this cannot be mutable, or yeah, and it's a little bit of a pain. So the nice thing is you do find bugs at compile time with that sort of thing. You also have some other language features that are sort of meant more for the safety type of things. One great example is match. So you write C, you probably used a switch case statement, works pretty well. Match is the Rust version of that. It's a pattern matching thing. But one interesting feature of it is, like other languages with functional features, whenever you have a match statement, it needs to match every possible case. We'll actually look at an example of that later, but that's the kind of thing that is a language feature that prevents you from writing potentially, sketchy code. There's good tools for it, and C is old and doesn't really have a single tool set around it. There's a million different things. Rust is new and has the benefit of having sort of the community and growing up in a different era. So there's things like Cargo, which is a package manager. There's a standard formatter. There's a ton of cross-compilation tools, which is what makes this stuff possible. And it also has a great foreign function interface to C. And without that, this wouldn't be possible. We need to be able to do two things, and that is call C from Rust and call Rust from C. And this is possible in a lot of languages, but it can be more challenging in some than others. But it does introduce a problem, and I will be perfectly honest that using Rust to write code for these systems is no silver bullet, like nothing else is. Because at the end of the day, you still need to touch memory in ways that is not safe. When we do this in Rust, we will need to put that code in an unsafe block. And there's a few things that we need that for. The big ones, this is actually straight out of the Rust book, the 4, but dereferencing a raw pointer. So whenever we actually want to get access to raw memory, we will need to be able to do that. So yeah, we need an unsafe block. Calling an unsafe method or function, well, it turns out that C methods and, C functions are going to be unsafe, so we're going to need it to call C. And then accessing or modifying a mutable static variable, that's like a global variable in Rust, matters less to us. And implementing unsafe traits is a language feature for actually doing like templates basically. And might matter to us as if we're trying to write bigger pieces of software. But the big ones are accessing raw memory and calling unsafe functions. But our goal can be to limit this unsafe code. We can kind of create very little places where we can do a lot more, a lot more eyes on it. We can do the minimal amount that we need to call those functions and do those types of things. Again, it's not perfect. It's not going to solve all your problems, but it does give you the ability to create separation between stuff that you know is dangerous and stuff that can be protected at compile time. If you want to learn Rust, these are some resources that are pretty useful. The Rust book is the place to go. It's online, it's free, it's nice. The second edition is the one you want. The paper version is coming soon from No Starch. It'll have that cute guy on the cover. Rust by Example, very useful website. You can run code in your browser, and it's really nice to play around with. It has basically every language feature. There's a page for it. So when you're like, I don't understand what the heck a trait is, there's a page that has a bunch of examples of when you might use those. There's also a woman by the name of Julia Evans, who her blog was the reason I first got interested in this language. She did this whole series on writing an OS in Rust and doing embedded stuff, low-level stuff. And I just think it's a really interesting series. It's like a fun, it's not boring to read. It's interesting. It's got pretty hand-drawn graphics. I'd highly recommend, if you're at all interested, take a look at her blog. Definitely worthwhile. So that's just a little bit about Rust and why we can use it, and then why we might want to use it. And now we're going to put the two things together. And there's a few steps. I'm basically just going to walk through how this ended up working. And the first step is we need an OS that we're going to run in the secure world. And there's a few different options out there, like I said, but at the end of the day, you're going to be limited by the things that you can get for free or cheap, and also the things that don't require confidential documentation. Because if you want to present at a conference, it turns out Qualcomm won't let you, put up their reference manuals on slides. So OptTEE, it's a free open source. It's from the Linero project. It works for a bunch of platforms and dev boards. You can they have this whole build tool. It is kind of magical. It does a lot of stuff, their build tool. But if you want to run it on a Raspberry Pi 3 or a BeagleBone or something like that, you can just basically say, I want the BeagleBone configuration, build, and it will just do it. It also runs in QEMU, which is nice because plugging a Raspberry Pi into a projector is not a great idea. It's well documented. It actually has public documentation, which is saying a lot. And it's got a website. So the first step here was finding an OS that would work. This one seemed to make sense because it's free, it's documented, I can use it and show you. So that was step one. Step two is to generate Rust bindings. This step terrified me. The reason being, that OS has a lot of functions you can call and a lot of types and a lot of other stuff. And I thought I was just going to have to write those all myself. And I was very happy when I found this bind-a-gen Rust tool. Basically what it will do is it will take some header files for a C library is what it's designed to work with. Take some header files. You put them, puts them in, and it does some, kind of magic. I mean, you can understand how it works, but it's nice. And it will turn those C declarations into Rust declarations. And this is an example of one going from C on the top to Rust on the bottom. So in C, you got the typical syntax: return type, function name, some parameters there with types, then semicolon. It's a function prototype. Whenever we swap over to the Rust world, the first thing you'll notice is the extern C around it, and that's telling us that it is in fact a C function. And then there's some syntax differences here. It's a public function, that's the pub. So there is, kind of like Java, there's levels of protection of those things. FN is our function keyword. Then we got the name of it. Then, kind of like Go, you got the swapped order of types and the names of the parameters, which is always a frustrating thing when you're going from C because you never get that the right way around. But you get used to it. So it's the name followed colon and then the type. And all of these types are actually now Rust types because every single type that was defined has also been implemented. And this deals with structs, it deals with unions, it deals with poundefs. It saves you I don't even know how much work. So whoever wrote this tool, I am very thankful that it exists. But what we end up with is this bindings file, which will let us basically have an interface to all of those C functions that we want to call. For example, if we want to initialize a message authentication code here, we can do that in Rust now. And then step 3 is you got to write some code. That's pretty straightforward, right? We're going to want to actually write our application. But we're going to write it as a library, not as an application. And that sounds kind of wrong, but it turns out these operating systems, they load your trusted application, and then they have specific symbol names that they're going to call at specific times, and you implement those. There's 5 of them for this one, and it will call those, and that's how you interact with the OS. So the way to do this is you compile a library, and then you link the whole thing together, and the symbols need the right names, and then it will actually be able to call them. So there's 5 functions that you're required to implement. There's a create entry point, which is when you first invoke this trusted application, that's going to start. There's the destroy entry point. That's going to be when you're done. It's going to clean up. Then there's open session entry point. So the application can keep running and have multiple sessions. On every one of those, it's going to call this open session entry point. And then when it's done the session, it will close session entry point. And then there's the one that we actually kind of care about for this example, which is the invoke command entry point. And this is whenever I'm in that normal world and I'm saying, okay, I would like the trusted world to do something. Here's a command code and here's some parameters. This is the function that's going to get called. So it's sort of it's the one that actually does stuff. And as an example, and this is sort of a proof of concept, I wanted to just implement the opt-TEE hello world, which is a really simple example. You give a number to the trusted application, it goes over to the secure world, it increments the number by 1 and gives it back to you. Pretty easy. There's another command ID, sorry, that's the 0 command ID. The command ID 1, same thing, decrements the number. So this is what that function ends up looking like, and conveniently it's nice enough to fit on one slide. So what we have there is this invoke command entry point. It's a public function. It needs to be so that it can be called from C. And then this definition is taken straight from opt-TEE's documentation. It's going to take these parameters. There's a session context gets passed. It gets a command ID, a param types, and some params. You'll notice that there's some unused variables here. Those are led with underscores. Otherwise, Rust will get mad at us for not using those. If you've written C and ended up writing macros that are called unused or maybe unused, and then had to do macro magic to make that work, this is way nicer. Then the syntax for this, we have a return type of the T result. That's the little arrow thing. And then this is really all it does. It's going to print that Rust TA invoke command entry point to say, hey, we're in the command entry point. Then we're going to do a match. And this I mentioned earlier as a sort of language feature. There's no switch case. There's match. And it's actually way more powerful than a switch case because it can do pattern matching, and it can do partial matches and all sorts of nice functional things. But we're going to use it in kind of a dumb mode and just match a number. So for each number, we care about 0 and 1. There's that arrow operator, and then we give it a block of code that's going to run. In this case, we need to go unsafe because we're going to modify a pointer, and then we take that param, the params, the dot value, and the dot a is actually because of how that struct is set up in opt-TEE. The as mute lets us mutate it, makes Rust give it to us in a mutable way, and that's where we need unsafe. So we're going to take that value, we're going to get it as mutable, and we're going to increment it by 1, and then we're going to print that we incremented the value. A few little things to note here. One, you'll see this TA print. That is a macro in Rust. The reason you know it's a macro is it's got an exclamation point. That means that it's dealt with by the preprocessor. This is a nice language feature of Rust. It's got quite a powerful preprocessor that if you've written C macros and spent a lot of time doing that, you might appreciate. I would recommend checking it out. And what that also lets us do is on these sort of lower power embedded systems, we can write code that does some simple things, but it can happen at compile time. And there's stuff that you just don't think about when you're not doing embedded code, like I want to append something to a buffer. And it turns out that that's more complicated than that can be more complicated than you thought when you're doing it at runtime. There's nice ways of doing that with a macro at compile time, which just saves you headaches. And then the last thing here is the underscore match. And that is the catch-all. That is the switch case default. And again, if I omitted that, if I just had 0 and 1, this would not compile. It would say something to the effect of match statement does not match all cases or something like that. You need to match every case. And that is frustrating until you realize that it's a good idea. And of course, we should return an error code, and opt defines error codes. BindGen generated all those for us. So hey, we got a semantic name for it, which is nice, and we can just return it. Otherwise, we're going to return success, and it's done. Really simple example. This didn't take me that long. This part took me a long time. This is actually getting the Rust code and the opt libraries and everything into a executable that will actually be able to load and run in the secure world on a real ARM system. And it's not that bad, but it had some caveats. But basically what we need as the inputs are 3 things. And this actually started off as source, but let's say we compiled them already. So we built our Rust library, and we have those 5 special functions that we remember from before that are going to be invoked. So that's built, that's compiled. It's like a .a, you know. Then we have to compile a TA header. There's a trusted application header. This is an opt thing. They have a special header format. You need a symbol with a special name that has like a UUID for it and a few other things. If you don't have that, it just won't work. Then we have some libraries that are provided by the operating system. This is libut, libmpa, and libutil. We're going to want to call the functions inside of there to do things like, well, even print to the screen, but also to do crypto and things like that. So we want to include those libraries. And then we have a linker script, which if you've ever wrestled with linker scripts can be not fun to deal with. But we have a linker script that fortunately comes from the project and with minimal modification works. And we take all that stuff and we give it to our linker. Our linker is then going to kick out a ELF for our trusted application. That won't work yet because we need to sign it. One of the features of the operating system is it will only run signed code. So fortunately they provide a script. You give it a stripped ELF. It takes that in. You show it where your private key is, and it will generate a signature, pop that on the top in yet another header. And then that is finally your signed trusted application, and that will run. And the first time I got this whole process to work, I was very happy. But yeah, it was just a lot of steps to all work. And just to show it working, because that's what you hope to do. This is going to look terrible because of the resolution. I'm sorry about that. But yeah, we'll kill it. So what we can do here is we're in a VM. We're in Linux because none of the stuff works on OS X. We're going to start up QEMU. And we are going to separate out these 2 windows. 2 things here. We got the normal world window. This is going to look like Linux, because it is. And we have the secure world window. This is just, it's not going to look like anything in particular. So first we have to make QEMU go. It should have done the trick. And you know, we got Linux booting over here, and we got the secure world just sitting there. The secure world normally would actually print out on something like maybe a UART, like a serial device, during debugging. But usually you're not going to leave that enabled for production for obvious reasons. You don't want to give people extra insight into the system. But in this case, conveniently, we can redirect that serial output into a window, which is quite nice. We need to log in as root with no password, of course. And when we run the normal world client application, which is actually the opt hello world example. We just run hello world. And what it says there, I apologize. It says invoking TA to increment 42, TA incremented to value 43. And then over in the trusted or secure world, we can actually see all the output messages from our application sort of around here. We have Rust TA, one of the entry points, and then it prints incremented value, and then it cleans up and it's done. So simple example, again, total proof of concept of, hey, can I get this whole thing to build, run, and link and actually work in TrustZone? And that brings me to a few sort of conclusions on this. Trust execution environments are very interesting. They're a useful feature for lots of stuff, but like anything else, they're not a silver bullet. You can still have all the same problems. They also have some specific challenges because typically the code you're running in there is going to be very limited, so protections might not be turned on, and we've seen, I showed a couple examples of when that actually was the case. Rust is a very interesting potential replacement, I'd say, for C in a lot of applications. And the reason is there's not many other languages that you can actually do this in without having to build a runtime and, or put an interpreter in there or whatever it is. But there's not many languages that you can actually compile straight down with no libc, nothing, and actually make work. And it has some cool added benefits. So yeah, there's this memory safety stuff that everyone's talking about. But there's also just nice language features. You get a better preprocessor, you get pattern matching, you get package management. All these features are actually quite useful even if the security part wasn't there. But you kind of get the whole thing. But really I'm kind of ending this with a question, because kind of the fun of doing these presentations and like playing around with these ideas, for me at least, is you come up with something and you try it, you make it work, and then you get to see what other people think and talk to other people about it. And so really I'm ending off with like should you do this? I don't know. I think that there's some interesting benefits of doing it. I've shown that I guess it's, at least in a proof of concept, is possible to do. There's probably some challenges, there's probably some difficulties, but I think it's at least something that's interesting to discuss, just given the amount of problems that we've seen in embedded devices and things like this where we have restricted execution environments and that whole thing. So I think it's an interesting topic. It's only going to continue being a problem as more and more IoT devices come online and things like that. So I think it's something worth discussing. Anyway, that brings me to the end of my my slides here and my presentation. I think we have about 10 minutes, 15-ish minutes left. So I'm happy to take questions either in a public forum or just hang out here and talk to you after. But thanks a lot to the Black Hat folks for having me back this year to talk about something other than cars. And thanks to all of you for coming out and listening through this. Hopefully it was of some interest and use to you. Thanks. Any questions? Well, I've always found that. Oh, question here. I haven't. Again, this is my first sort of publicly talking about this whole project anyway. So, but I'd be interested. And maybe their answer is no, that's a stupid idea, but I'd love to hear why. And I'd love to have that debate. And yeah, I think that, again, I think it's something worth discussing, but I haven't talked to any of those folks, unfortunately. If any of them happen to be here, I'd love to talk to them. Yep.
I've got another question about trust execution environment. Do you have some recommendation on how to save data in this? I understand how to protect application, it just seems right. But if you want to save something or use some sensitive data, I don't know if there's some, it's a process or feature, so there is no security storage. How to manage this?
Okay, the question was, how do you do secure storage, in this trusted execution environment? Because yeah, we can protect the execution, but at the end of the day, if I'm going to write to the disk, everyone can see it. And so the way that that's typically done is and this is again where you get into the chipset specific, NXP is different than Qualcomm and no one will tell you how it works. But there's features that either have a special key that you can read. So there's like a encryption key that's unique to that specific chip. And I mean like that one chip, it's randomly generated when the thing is fabbed. And so either you can get a key from that, or they have a security controller that's capable of doing encryption and decryption operations using a key that can never be read out of the device. It's also randomly generated for that specific device. And so OptTEE actually has a whole implementation where, first off, actually, before you even get into there, you have to set up the processor so that whatever that key material is or that oracle is, it's only accessible from the secure world. So That's the first thing you need to do. Otherwise, anyone can decrypt. Once you do that, you can actually set up the operating system to do storage where it uses that key. And they actually kind of do it in a smart way, so it'll take that key plus some other stuff, plus the UUID of the application and generate a per application key, so that theoretically you can't read other applications' files. And once it has all that, it will actually just write it. There's a few ways to do it, but the default is it just writes it to the Linux file system somewhere. And yeah, the file's there, you can read it, but it should be theoretically impossible for you to get the key to decrypt it. Now, it's not in a lot of cases, because if you can control the device and you can boot the thing up in in a controlled way, you can probably get access to those keys. But the benefit there is that there's a different encryption key on every single one of them, so unless you're holding the device in your hands, it's pretty hard to compromise the whole thing. So that's typically how it's done. That's at least how OpTEE does it. There's also a similar setup in the Qualcomm QC operating system, where it just writes to some different places, but it's a similar idea. It's using this per device hardware key to generate that key material.
So now in this TOS, it's not implemented really. So no encryption, nothing but this environment to start that application.
Yeah, so by default, there's actually a lovely wiki page in the OpTEE project where it's like, warning, this secure storage does not work by default. Which is a nice warning for them to give you. But yeah, it says, you need to implement this function to do the encryption and decryption, and we can't implement that for you because the information on how to do it is under NDA. So we can't, open source that implementation. There may out there be some open source projects that may have some implementations of certain ones, but you really got to hunt for them, and yeah, it's a little sketchy. But so unfortunately by default, the file secure storage stuff, SFS and the RPMB storage are not actually secure. But if you implement the stuff according to the application guide, you have that relationship with your chip manufacturer to get the right information, you should be able to put a very solid system together. Cool. All right. I don't see any more questions, but I will stick around if you want to ask me anything personally. But yeah, thanks again for coming out, and hope that was useful.